Hello everybody, up games, and welcome back to our tutorial about simple genetic algorithms in Unity. It's been over a year, sorry about that. I was very busy with school, but now I've graduated, so got more time now. So let's get back to it. First of all, I've updated my version of Unity here, so like this will work probably on any version of Unity. And the last time I made a couple of mistakes. First of all, here in the DNA class, in this constructor, I was supposed to type dot add parent genes and add partner genes, but I accidentally typed parent 2 times, so you can change this to partner if you haven't already. And then in the genetic pathfinder, I created this path multiplier variable, but I never used it anywhere, but it's supposed to go here. So when we are adding the next gene to the path, here we're multiplying with the path multiplier. And yeah, those are the mistakes. And let's get to improving this stuff and making sure they can find their way around objects and stuff. But first, we will do some, would I say, make stuff look nicer. So first, we're gonna create a public quaternion. That's gonna be it's just a helpful function to help us rotate easier. Just gonna take vector3 target, 2 target, and vector2. Oh, it's just gonna take target, and then it's gonna take a float. That's an angle offset, which is gonna be 90. And then we're gonna do vector2 called from 2, and that is equal to target minus position. Target that position and transform that position. Sorry about that. And we're gonna cast this to a vector2 like so. After that, we're gonna normalize, or just let's just put this in bracket like this, and say normalize. Then we're gonna do a float cut z rotation. It's gonna be equal to mathf dot attend2, and how you're gonna supposed to say that. Then you get to from 2 dot y and from 2 dot x, and 10. Then it's times mathf dot radians to degrees. So rad to deg, no brackets, like that. And then we're just gonna return quaternion dot Euler 0 0, and then rot z z rotation times a plus angle offset. Yes, there we have it. And that this will, it's, even though the look at function in Unity, this is the same, basically the same for 2D objects. I don't know why Unity doesn't like, or I haven't found a way to do it like easily, so I just use this all the time. It's pretty good. And then when we set the next point, let's just do a quaternion, and that's target rotation. And then here we're gonna set the target rotation, so target rotation is equal to look at 2D, and then we'll just input the this after this, so we can just put next point, and then yeah, just next point, and then we'll do here. Oh, let's just do it here. If transform that rotation is not equals to target rotation, we are going to rotate. So quaternion, let's slurp, and then let's do transform rotation and target rotation. Then we have to, but let's just make a public float. Rotation speed doesn't affect the movement, but it's just like how it looks. So that will rotate towards the next point. Let's just put like rotation speed times time dot delta time. Yes. Okay. So let's test that. And after all the changes, you can see what's different. I've changed the path multiplier to 1.5 here on the creature. Yeah, let's test it. I don't see any rotation. Why is that? Oh yeah, of course. It seems I have forgot to actually set my transform. Transform that rotation is equal to this. Yes. That was awkward. Oh, of course. Another thing, I didn't set the rotation speed to anything. So let's just set the rotation speed to something like 30 maybe. I'm not really sure how fast it's gonna rotate. Let's decrease the creature speed so we can actually see what's happening. Maybe 15 and 25 so we can see what's happening better. There seem to be a couple of problems. First of all, the angle offset was supposed to be minus 90, not 90. And second of all, I actually didn't set the rotation of the object. Oh. But yeah, now if we just go here and change the speed to like 25, you can see they are actually facing the way that they are going. Yep, that was just a little like graphical update. And next, let's add the line renderer. So just go here, add component, and a line renderer. Let's do that, and let's set another key here, and set this point down here, so that when there's actually a line, they will taper to the end. Like, let's see. Is there material? No. Just default line. Material. Yeah, there you can see it. Let's delete that. And then when we are in our genetic panfinder again, let's make a line renderer called LR, and then let's set LR in the init creature to get component line renderer, and then let's just do a public void render line. And then we are going to create a list of vector2s called traveled path, and equal new, a list of vector2s. And then every time we set the next point, okay, first of all, when we start, we're gonna do a traveled path dot add transform the position, transform that position, like so. And then every time we add the next point, travel path, we have to do this, the travel path dot add next point here first, next point, and then every time we change the next point, we are going to add the next point to travel path. Travel path dot add next point. And then here in render line, we are going to for int I is equals 0, I is less than travel path dot length, travel path dot count -1 I plus plus. And here we're going to another list of vector2s called line points, and that's going to equal to a new list of vector2s like that. And then in here we are going to line points dot add travel path dot I, and then line points dot add transform that position, and then we're gonna say line render that set points positions, and I can remember it's just gonna take it's gonna take in an array, so we're just gonna put line points dot to array like that. Oh, it doesn't like vector2s. Really? Can I cast this? No, I can't. Okay. So in that case, we're gonna do this. We're gonna be a list of vector2s, trees, I guess, and then line points dot to array. That works. Okay, we'll just do it that way then. I'm not sure if this works. Let's. I never called render line, and there is actually another problem here. let's say if travel path dot length dot count is less than 2, it's less than 3. It's 3. Oh, we're gonna do this. Is more than 2. Yes, yes. We're gonna do this. Else, we just gonna add travel path. It's the first element in the array and on the list. Line points dot add, like so. And of course we're gonna add the our transform position after that. And then let's call the function here. So render line. Now let's test it out. No errors. I don't see any lines either. Position count gets set, yes, is equal to line points dot count. We have to do this before the set positions. Yes, yes, of course. And somehow works. Somehow works. We're just gonna have to change some things here. Let's put this to 0 for now. And this can be 0.1. Let's test that again. Still so fucking thick. Even smaller. And I guess like we don't have to do this. Probably let's just see how it looks without it. Yeah, that actually looks better. And after that, we're just gonna put a nice little gradient here. Just choose like 3 colors. Something that looks cool. Purple. Then like a red. Yes. Now it's look all cool. Yeah, there we go. There we go. And now that all that's done, we are going to start working on the actual collision detection. Or the collision avoidance and how they're gonna learn to avoid obstacles. So for now, uh, let's just don't not drag into the creature, but go back to the scene and drag it into the scene. Let's drag one of these cubes here. And let's just like make it some arbitrary size. Let's rotate it a bit or something. Let's do that to have an obstacle there. And then let's add a box collider 2D. I think that's, oh, oops, didn't mean to open that up in Photoshop. Just open this, and no, we're just gonna add a collider then. Let's use a capsule one. I like capsule colliders. Just this to the size. Should be okay. And then let's create a layer called obstacle. And then let's add a rigid body 2D here, and let's make it like a static one, I guess. Yeah. Let's just make a kinematic one. And let's change its layer to obstacle. And then in the genetic pathfinder class, we'll add a void on trigger on collision enter. Let's just do it on trigger enter. On trigger enter 2D. If collision layer the game object layer is equal to, let's check, number 8 is 8. Has finished is equal to true. Yeah, so let's just try that for first. I know this is not gonna it's not gonna be perfect yet, but we're gonna improve the fitness function just in a bit. It's just like will already be much better for now for some time. Now let's just increase the speed of our creatures back up to 550, so 50, so we don't have to wait forever. And let's just put genome length to 50 also, so it doesn't take that long. Now we just watch them learn a bit, and then they will start getting stuck on the or not. Oh yeah, of course, of course, of course. I never set this to the trigger. Now it should work better. But let's also make sure that these are the other layers one, so it will be displayed over stuff. And let's just make it a little like bluish, so we can distinguish it from the obstacle itself. Yeah, now they will, if they collide, they will be stopped. And as you can see, that this actually is enough for them to get through this simple scenario, because if they collide, they're probably not going to get that far. But there are more complicated scenarios where they will just evolve to get stuck. So we're going to address that. So let's just make more of these obstacles here. Let's try something like that. And like this kind of situation is a little bit more complex, so they will probably never evolve to get over it, or maybe they will actually. Yeah, they will. Yeah, I was wrong. Let's just add one other block here. So something like that. Interesting is silicon intro. It's pretty good. I'm surprised. Guess life finds a way, even if it's not an actual life. It's amazing. Yes, here you can see a scenario where the genetic algorithm has found a local minimum. So how we can combat this is by, when we have this is finished here, we're gonna also make a bool, because has crashed, and that's gonna equal to false in the beginning, and only when we crash into a thing we have will put like has crashed to true, because this is has finished is true, will be true if it's in the end of its path or if it has reached the goal, but this will only be if it's crashed. So now in the fitness, we're gonna do this. Just gonna make put these into brackets, make it times and bracket, another brackets, and inside here we're gonna do a has crashed question mark, and this is another way to do an if statement. Basically, you put a condition. So this has crashed. It's either true or false. And if it's then I put a question mark. And if it's true, it's gonna take the right side answer, and then we're gonna put semicolon. And if it's not true, it's gonna take the other side. So if has crashed, we're gonna return a fitness that is times 0.7, and if it's not, we're gonna return times 1. So if it has crashed, it will have the 30% less uh, worse fitness. It's 75, 25% worse fitness if it crashed, and if it doesn't, it has its full fitness. So this way, it can like help the genetic algorithms to solve problems that they otherwise would get stuck on. So let's just watch it. Let's hope they will get through. Yeah, still pretty hard. So, let's change this penalty to like 65, and let's increase our. Is there? No, we don't actually have that. Let's add. Where do we do the population size? DNA. Here, a mutation rate. Mutation. Mutat. mutation rate. Yes, and then just add a public float mutation rate. Let's make the slider range from 0 to 1. Yeah, mutation rate, no mutations rate. Yes, it takes care of the problem. So then to further make our fitness function better, we can still do more. So let's add a public layer mask. Oh, not late update, but layer mask. Um, and that is called obstacle layer, like so. And then in our fitness function, we are going to create a raycast to hit 2D array, and we'll just call that obstacles, and that is equal to physics 2D the raycast, and that's gonna take it transform that position, and then target, and then we're gonna pass in our obstacle layer, like so. Raycast all. Sorry about that. It's supposed to be a raycast all. And then we are going to do a create a float, and let's just call this obstacle. Uh, what should we call this? It's an obstacle multiplier. It's gonna be 1 minus let's do 0.1 times obstacles length. Just do 0.15, and then we're just gonna time this by the obstacle multiplier. And that should already be much better. So let's just test it out. Let's actually increase the speed yet again. Let's put it on 500. 100. The path multiplier is going to be 2. And then let's just do population controller. Let's set the mutation rate to 0.05. And let's try it, test it. They're gonna go pretty fast. There's still one more thing we can do to improve this. Yeah, now it should not get stuck on that ledge there. Or it might still, but like much less so. Because like now it checks how many obstacles is between it and the end, and basically decreases the fitness if there's like the more there is obstacles in between. Yeah, now let's do the final improvement. So actually we're gonna go to our population controller now, and in the next generation, when before we do this whole thing, we just gonna like take the first 5 or 3 order of the survivors. So let's just say for int I is equal 0, I is less than 5 for now. Okay, cut off. Let's just put another like public int, and that's gonna be survivor keep. Yeah, let's name it that. It's gonna work anyways. So here, which is survivor keep, and then I plus plus. Close that off with square brackets. No, not square brackets, it's squiggly brackets. But yeah, and after that, we're just going to say population dot add. Yeah. Okay, of course. We have to do this. Let's copy this. Just instantiate creature like this, and then we're gonna go that get component genetic pathfinder that DNA is equal to survivors I dot DNA like that. And then let's say, well, let's just go actually. Let's go the and make another initialize function. No, we don't. We don't need to do that because I just can't remember my own stuff. So it's just like initialize. Yes, we're just gonna pass in this and the end point dot position like so, and then we're gonna get to do a population that add go that get component genetic pathfinder. Yes, and this will do sort of like sometimes when this runs, there's like a creature that's pretty damn good, but then because like it dies and the next generation mutates too much or the crossover doesn't work out, it just the improvement isn't kept and it just like goes away. So this way we can at least make sure that the top 5 survivors like don't get wiped out and they will be put up to the next round. So any improvements made are kept. They will keep improving. And yeah, now it should be much better. We'll just let it run for a while. Oh, sorry. One thing I actually forgot to do is go to the prefab here and change, yeah, obstacle layer to obstacle. Obstacle. Did I do that? I don't remember doing that. I guess I did. Yeah. Uh, that's it for the basic genetic algorithm tutorial in Unity in C Sharp. Long been due. Now that I have more time, I'll probably do some more tutorials on genetic algorithms and such in Unity. Maybe some basic game dev tutorials also, since that's what I graduated as. Like, leave a like if you liked the video. I'll learn something new. Subscribe if you want to see more in the future, and if you have any suggestions on what I should do next, leave them down below in the comments. Thanks for watching. Bye bye.